Hi friends, today we are going to see a new topic in multi-rate signal processing which we called as digital filter bank. So today we'll see what do you mean by digital filter bank. So in digital filter bank, okay, as we say that filter bank, that means there will be series of filters or there will be many filters and they all will be digital filters, they will not be analog filters. Basically, there are two basic types of digital filter bank. One we called as analysis filter bank and the second one we called as synthesis filter bank. Okay. Now, why we have this two sets of filter banks? One, if I wanted to analyze the spectrum, okay, we can do spectrum analysis, or we can see that how many components are there in x of n and so on and so forth, or we can break down x of n, one input signal, into many output signals or many outputs. So, if I wanted to go deep, dig deep and see what the signal looks like, then we normally use analysis filter bank. If I wanted to just synthesize a signal, then we will be using synthesis filter bank. So here it is spectrum analysis, here we called as signal synthesis. Okay. So here what it will be? It will be one input and many outputs, that is analysis bank. Synthesis bank, many inputs, one output. So you can say it could be like it is similar to that of multiplexer and demultiplexer. It is not same. I am not saying it is same as that of multiplexer and demultiplexer. You can just make an analogy that analysis filter bank act like a multiplexer, or it is same, or it looks like a multiplexer which has one inputs and many outputs. Okay. It does not say that one input will be corresponding to one output only at a given time. It is not so. We will get outputs at all the values, all the outputs. Okay. So one input, many outputs for analysis bank, and many inputs, one output for synthesis bank. So how the bank will look like? You can now immediately draw the banks. We have one input x of n, which will be now splitted into various banks. Okay, let's say this to be h of 0, this to be h1 of z, and so on and so forth till I reach to h, let's say n of z. So how many total values? H n minus 1 I say, okay, because I am starting with 0. So total n components I have, and it starts from 0 and ends till n minus 1. Each of them will produce an output which we called as y1 of n, y2 of n, y3 of n, so on and so forth, or yn minus 1 of n, because it is the last sample. Okay, fine. What will be synthesis? Many inputs will come. Let us say that all y's are going as an input, and then I will have an output. It does not mean that I will have a analysis and immediately a synthesis. This is a very rare case, and we will use kind of a scenario where I will have an analysis bank and a synthesis bank together, immediately connected, cascaded. But many a times it might happen that I analyze the signal at n different stages and then I synthesize the signal at some other stage in the process. Okay, so they might be far apart, and they will be getting inputs from some different in between systems might be. Okay, so I have a analysis filter, and in synthesis I will have and then they will all sum up together into an adder to produce a particular output. Let us say x of n, and I will get y of 0 of n y1 of n and yn minus 1 of n, sorry, not z, n. Agreed? So this is how analysis bank and a synthesis bank look like. Let us dig deeper into this. Next, let us understand that how to make this n analysis bank. If you will have looked closer, I have written something like this. The filter transfer function, let us take analysis bank. The filter transfer function that I have written is h0 of z, h1 of z, h2 of z. How to obtain the characteristics of h0, h1, h2 and so on and so forth for n characteristics? The simpler method is, we will be using DFT. So, let us do a DFT. Okay. In a DFT, what I do is, I design a prototype filter which we called as h0 of z. So, h0 of z becomes my base prototype, which is not now, it will not no more be called as h0 of z, it will now be called as h0 of omega, hk of or h0 of omega. It will be now called as h0 of omega because I have Fourier transformed it. Okay. Now what I do is I shift my signal, okay, or not the signal, the transfer function, let's say by a factor of 2 pi by n. So the total shifts, you know that omega is a complete circle which will start from 0, end at 2 pi. So now my omega is having an interval of 0 to 2 pi, and this frequency spectrum I will divide into subsets or subparts. If I divide into 8 parts, what is going to happen? If say this is a first point, then this becomes my second point, this becomes my third point, this will be my fourth point. Let us say they are equidistant, fifth point, sixth point, seventh point, and then again 8 point, isn't it? So that means 8 total values, that 0 to 7. So this is 0, this will be 1, 2, 3, 4, 5, 6, 7. You can go in the reverse order also. I have chosen just to give you the flavor that what actually DFT filter bank means. So I am using DFT. Why I said DFT? Because we are dividing omega into n further subsamples. So I have sampled the omega into n regions, or in this case into 8 regions. What will be each angle? Each angle will be 2 pi by 8, isn't it? Total is 2 pi. I have divided into 8 subparts. So it will be 2 pi by 8 each angle, and I will have the first value as 0, second angle will be 2 pi by 8, third angle with respect to 0 will be 2 times of 2 pi by 8. This point will be with respect to this. So this is 0, this is 1, this will be 2, this will be 3, this will be 4 pi by 8, and so on and so forth. Last value will be 7 pi by 8. When I say 8 pi by 8, I am again at 0, which is the same point, or 2 pi, which is the same as that of the 0 point. Okay. So my prototype is working at h0 of omega. Let's say my first value, that is h1 of omega, is obtained by shifting the whole transfer function or whole frequency spectrum by a value of 2 pi by 8. So I will now have h0 of omega minus 2 pi by 8. Okay, that is first I am using what? DFT, because I am frequency sampling. What I am doing is I am shifting the whole spectrum by some factor. That factor is 2 pi by 8 in this case, because we have considered to divide the incoming signal into 8 subparts. Then I have h2 of omega, which I will write as h0 omega minus, I will write 2 pi by 8. Okay, but now I will write it as 2 pi by 8, and so on and so forth. It will go to n minus 1 pi by 8. Okay. So in general I can write hk of omega to be equal to h0 omega minus 2 pi k by n. So we have seen that we have different transfer functions of the filter which are derived from one transfer function which we called as a prototype. So h0 of omega is called as a prototype filter or prototype transfer function, and when we go on shifting it by k values, we are going to get hq of omega. How they look like? Suppose this is my omega scale, okay, and I have the prototype transfer function going from minus pi by 2 to, let's say, pi by 2. Okay. Then now I will shift the first filter to, let's say, at 2 pi by n. So the first point will come at 2 pi by n. Okay. Where will be the lower limit end up to? Oh, sorry, it's not pi by 2, it's pi by n. It's pi by n. Oh, I'm extremely sorry, this is not pi by 2 because I have not considered any value for I. So let's say pi by n. The next shifted version, that is h1 of omega, is centered around 2 pi by n. Its lower and the upper limit will be like this. Okay, it will be similar to that of this. I have drawn it enlarged, but it is not so. It will be very similar to this much. Okay, so this is h0 of omega, and this is h1 of omega, and so on and so forth. I will have hn of n minus 1 of omega, which are just shifted replicas of h0 of omega. This type of filter bank, which uses uniformly shifting DFT, is called as uniform DFT filter bank. Okay, so we generalizely write it as hk of omega equals to h0 of omega minus 2 pi k by n. Okay, where k will run from 1 to n minus 1. Okay, why it will not take 0? Because h of 0 itself is the prototype. When you put 0 over here, it is h0 of omega, which is the prototype. Okay, if I wanted to write in time domain, then this I will write as h0. This is h0 of n equals to h0 of n e raised to j 2 pi n k by n. If you remember, I have used inverse Z transform to achieve this, and while I am using inverse Z transform, I have one property implied over here. We see that the frequency is being shifted by 2 pi k by n factors or with some integer. If I use this factor, that means there is a frequency shift, and according to the frequency shift property, if there is a shift in the frequency range, or if there is a shift in the frequency domain, then the immediate impact on the time domain happens is we need to multiply by a phasor value, which is e raised to j 2 pi n k by n. Okay, so there will be a phase shift. There is a phasor factor will come into picture. So this is what my time domain filter will look like. Okay, how will I implement them? Very simple. For analysis bank, let's say I have x of n. Okay, I need to translate them first What is the translation? I need to actually have e raised to j 2 pi n k by n in place. How will I do it is, I will imply a multiplier, okay, whose next input is e raised to minus j, okay, let's say omega 0, okay, omega 0 omega 0 of n. Next comes as e raised to minus j omega 1 of n, and so on and so forth. The last factor will be e raised to minus omega n minus 1 of n. Okay. Then I will pass them through h0 of n, here also h0 of n, h0 of n, okay. And then let's say that if suppose you wanted to decimate, then you can apply a decimator. If you want to increment, you can apply an incrementer or something like that, okay. So what I am going to do is, I am going to decimate the system. So let's say I have a decimator on each row. This is not exactly what is needed, okay. We are just putting a system. So we have analyzed the signal by breaking it into subpoints. That means x of n is now broken up into pieces, and each piece is going to get decimated, and at the output I am going to get decimated different types of decimated samples. Okay, so this is what is happening in the DFT analysis bank. Similar thing will happen if I consider a synthesis bank. In synthesis bank, if I use the same concept of DFT synthesis bank, then there will be the opposition or opposite flow. First I will get some, let's say y1 of y0 of omega, y1 of omega, I'm sorry, it's not omega, it's m. Let's say I'm going to input as y0 of n, y1 of n, so on and so forth, yn minus 1 of n or m, whatever. First we will be passing them what we did previously, we decimated. So what we have to do here is interpolate to get the original signal back. So to interpolate, the factor by which I decimated the signal in the analysis bank, the same factor I will use to interpolate in the synthesis bank. So my interpolation factor I will be equal to D in this case, because I wanted to recover the signal. This will not always be the case. It might be or it might not be. In this case it is so. So I will have an interpolator with factor D only, because I is equal to D in this case. Then we will pass them to filtering to avoid images. Let's say this to be GO of n, G1 of n, and let's say this is Gn minus 1 of n. Then what I have to do is, I have to again frequency, translate them. There we have done some translation, so here the same translation has to be done. So synthesis and analysis are just reciprocal to each other. Whatever we do over there, the reverse operation we have to do over here. So I will have e raised to j omega naught n, e raised to j omega naught omega 1 n, and so on and so forth, e raised to j omega n minus 1 of n. Okay, and then we will add them all. This will produce x of. So from this structures, what I can say is, when I am doing analysis, I have broken the x of n signal into its components, translated them in frequency by keeping e raised to minus j omega 0 1 0 omega naught omega 1 omega n minus 1, which are shifted versions of omega naught, then passed through a filter which is h naught of n, and then downsampled it. Let's say I operated over here as downsampling, so that's not a problem. So I downsampled the signal because I am using decimator. Now suppose I wanted to recover x of n back from x0 of m's. Let's now write it of x0 of m n minus 1. Let's say after x0 of n minus 1 has been obtained, we give this signal to something else system, and from there everything comes as an output as y's. So here we have y0 to yn minus 1 of n, which are coming from intermediate steps between analysis filter and the synthesis filter. Okay, it might not be that I have directly connected them both. Okay, now once I got this, what I have done over in the analysis, the reverse order I have to do. If I it's like encoder decoder. If I've encoded there, I have to decode to get back my original information. If I want my x of n originally back to me, then I have to give the y0 to yn minus 1. There I have downsampled it. Here I will upsample it. There I have downsampled by a factor of d, so I will now here upsample by the value of d itself. Because I am upsampling, there will be images in this images in the signal. To avoid the images, I will do filtering. So I will use filtering. There I have translated the inputs, so I have to retranslate them or bring them back. So I will multiply by e raised to j omega naught d, and then finally we will add them all and get back the information. So this is the synthesis bank, and that was the analysis bank. And this way we apply the concept of digital filter bank in multi-rate signal processing. I hope you have understood how and what are analysis banks and